Kramer here. I'm going to give you a summary of Chapter 18 in this video. It's called Chemical Bonds, but I wanted to do it with a little bit of entertainment, so I'm going to sit at the drum set while I give you this understanding of Chapter 18. If you don't already, hopefully it will improve your understanding of Chapter 18, and maybe you'll even enjoy this lecture more than you otherwise would. Obviously, I have the periodic table set up here behind me. I've got my drum set around me, and I've got this PA just to trick things out a little bit. So anyway, Chapter 18 is about chemical bonds, and I'm gonna try to use this over here next to me so that I can play the drums while I talk a little bit. Maybe. Okay. Move it down just a hair. There we go. Okay, so Chapter 18 is all about chemical bonds. Now what are the two big categories of chemical bonds? One is ionic, and the other one is covalent. Chemical bonds make compounds. They don't, chemicals, elements, atoms react with other atoms by interactions at the outer electron energy level. They don't make chemical bonds from nuclei to nuclei. The nuclei have nothing to do with the chemical bonds. The nuclei are just sitting there happy to exist. And chemical bonds are only the combination of electron clouds where electrons are either stolen or shared with a neighboring atom. So if the electrons are shared, it's a covalent bond, and if the electrons are kind of sort of stolen, so that when you're in a polar solution like water, a bipolar solution like water, you can actually dissociate. The two different atoms will actually dissociate rather than be stuck next to each other like the north and south pole of a magnet. So anyway, just a thought. There's section 1. If you'd open your book to page 552, what I'm about to, the things I'll be saying here will make more sense, and we'll move along according to what the book says. So anyway, elements lose a molecule looks a lot different than the elements that make the molecule. The physical characteristics of a chemical in a chemical bond change the way things look, smell, etc. So the elements lose their initial characteristics. Let's see if I can play some drums and make this more interesting. Here we go. Anyway, that was funny. All right, so chemical bonds. Let's see if we can make it more interesting. You'll notice on page 554 at the top, they are showing part of the periodic table. They're showing rows 2 and 3, which are pretty normal elements to find in nature. And you'll notice that there are things that don't react. You'll see the electron dot diagrams for the noble gases over here on the right here. These noble gases don't react with anything. They're fat, dumb, and happy because they have a full outer level of electrons, and there's no reason for them to make a chemical reaction with anybody because they're completely satisfied in a satisfied state. The potential energy of a full outer level electron cloud is very low, and so it's difficult for them to decide to react. It's hard to get them excited. It's hard to get those noble gases get their electron cloud excited enough to either share an electron of their own with another atom, or to receive an electron from another atom. So they're very stable, is probably a good word that's used in this book. Very stable. Non-reactant is another big word, okay? So anyway, then we can see these other elements that are gaining an additional electron. Back up at the top of page 554 in figure 3, what you see is from left to right, you see the outer level, the outer energy level of atoms gaining an electron. Lithium is in this group right here, up there in row 2, lithium. It has 1 electron in its outer energy level. Then you see beryllium. It has 2 electrons in its outer energy level. Here's beryllium up that column, okay? Right next to lithium. And then you have boron, which is over here. Right there. Right there's boron. It has 3 electrons in its outer energy level. Carbon has 4 electrons in its outer energy level. Nitrogen has 5 electrons in its outer energy level. Oxygen has 6. Fluorine has 7. That's 1 away from a full outer energy level. So it's very excited to get an electron from somebody else, just as lithium is very excited to give up its electron. And then there's neon, which has 8 electrons in its outer energy level, and it's not going to react with anybody. Woohoo! Let's move on. Table set up. It's organized very well. You'll notice there's periodicity in a periodic table. So that one period 2 or row 2 of the periodic table is repeated in period number 3. You'll look at sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon moving across in level 3, and then it repeats again back down into row 4, right? Now the row 1 is kind of special because the first energy level of electron clouds only has 2 electrons in it, and so hydrogen and helium have that specialty role up at the top, where hydrogen is over here with the group 1 elements, and helium is put over above the either the group 18 elements, or I used to call it the group 8 elements, but that's that's not done in this book, okay? Now, let's talk about chemical bonding again. We have, on page 555, an example of sodium chloride. Now, you'll notice sodium has 1 electron in its outer energy level. It has 8 electrons in its level 2 electron energy level, and it has 2 electrons in its level 1 energy level. So sodium has 1 electron in its outer energy level, and it wants to give that away as fast as anything. And chlorine, you'll see, is over here in this column. It has 7 electrons in its outer energy level. It has 8 electrons in its second level, and 2 electrons in its first level. So 2, 8, followed by 7. And it really wants to get an electron, bad. It wants to get 8 electrons in its outer energy level, just as sodium wants to get 8 electrons in its outer energy level. So sodium gladly gives an electron to chlorine, and chlorine gladly receives an electron. And now you have sodium chloride. But the electron spends so much time over in the chlorine atom that sodium chloride will dissolve in water. So then you have sodium plus ions floating around in water, and chlorine negative ions floating around in water when sodium chloride is added to water, okay? And so this is called an ionic bond. Sodium and chlorine are not sharing that electron. Chlorine has taken it, if you will, from sodium. And sodium gladly gave it up, and chlorine gladly took it. And now both sodium and chlorine are more stable because they have 8 electrons in their outer energy level. Now, if we turn the page to page 556, you'll notice oxygen bonded with 2 different hydrogen. Oxygen has 6 electrons in its outer energy level, and it wants 2 more. Hydrogen has 1 electron in its outer energy level, and it wants 1 more. So when you have 2 hydrogens and an oxygen making H2O, or water molecules, then you have oxygen happy with 8 electrons in its outer energy level, and you have hydrogen happy with 2 electrons in its outer energy level, okay? Both have full outer energy levels, sort of. This is what's called a covalent bond, because hydrogen has an electron from itself and an electron from oxygen, sometimes sharing its outer energy level, and then sometimes oxygen has the hydrogen electron in its world, in its atomic environment. But neither oxygen nor hydrogen want to give up the electron and oxygen take the electron as much as in sodium chloride bond. So these electrons are shared from one atom to the other. And so because they share the electrons, sometimes the electrons would be more hanging out and orbiting around the oxygen atom nuclei, and sometimes one of those electrons from oxygen are hanging out in the electron cloud around hydrogen. So this is a covalent bond. It does not break apart in water, okay? There's lots of covalent bond examples. Okay, so sharing electrons and chemical bond formation. So section 2 is talking about types of bonds again, ionic bonds being the transfer of electrons, and they give a great example in potassium iodide. Take a look. How many electrons are in potassium's outer energy level? 1. And how many electrons are in iodine's outer energy level? It has 7 electrons in its outer energy level. And so the 7 wants to become 8, the 1 wants to become 0, so the outer energy level becomes an 8. and then potassium iodide is formed. And you've heard that term before, I'm sure, potassium iodide. You can find that in that salt, sea salt, iodized sea salt, right? Potassium iodide is there in that food, spice you could call it, okay? So anyway, that's a great example of the giving of electron to the other atom, okay? And that's an ion, that's an ionic bond. And there's a lot of discussion here on page 560 about ionic bonds. Here's a magnesium chloride. Another example, I believe this also is ionic bond. Magnesium is wanting to give up 2 electrons, so it will actually bond with 2 different chlorine atoms, and both chlorines will take an electron from magnesium. So if you put magnesium chloride in water, you would end up with magnesium floating around as an ion, and chlorine ions floating around. The magnesium would have a positive charge of 2, and the chlorine ions would have a negative charge of 1. Atomic, or that's elementary charge. The elementary charge on an electron. So anyway, so you have ionic bonds, and you can see that this group 2, the alkali earth metals, will actually become a 2+ ion in water, especially the ones closer to the top of that column. I guess they'd all go to a 2+ if they were reacted with a halogen, or these ones with 7 electrons in the outer energy level. These guys reacted with these guys, become ionic bonds, okay? So then we're talking about molecules now on page 561. You've got H2O again, talking about how that works. You've got nitrogen that is triply bonded to itself in our atmosphere, and you've got oxygen that's doubly bonded to itself in our atmosphere. So these are nonpolar bonds. There's equal sharing of the electrons, because obviously one oxygen atom can't pull on the electrons harder than the other oxygen atom, or one nitrogen atom can't pull harder than another nitrogen atom. So when you've got these these diatomic bonds, which form a lot, those will always be covalent bonds, because there's equal sharing of the electrons in those kinds of bonds. Okay? When there's unequal sharing, it gets so unequal that it becomes an ionic bond, and then there's also unequal sharing that's still considered a covalent bond. For example, H2O, okay? So there's some bonds are so polar that there's unequal sharing to the point where it's an ionic bond, and then there are bonds, covalent bonds, where there's unequal sharing, but they don't ionize in water. So they're not called ionic bonds, they're called covalent bonds, okay? Writing formulas and naming compounds will be next. I'm on page 564 and 565. Okay, so I used to be really good on the drums, but now I'm just a hack. So put up with me a little bit. I love you. Hey, I just thought of a song. My Corona. My Corona. Very good. So, I just sang My Corona, if you couldn't hear me. Anyway, it looks like our nation's going to open up. We haven't heard yet from our governor, Holcomb. I'm neither surprised nor frustrated. Governor Holcomb's got a big job to do. He's probably not qualified to make the call about opening up the government. Not opening up the government, opening up the state. And so he's having to depend on other experts that he has around him, and he's decided to surround himself with. And so that's a tough position to be in, especially when not all the experts are in agreement. There's probably not consensus among the experts. And so Governor Holcomb's going to have to figure out and become qualified to make the call. And that's a hard job. I've had jobs like that where I had people that were trying to help me to make decisions about, what's the next step to make things better than they otherwise would be. And a lot of times experts don't agree, so you have to study why they think it's a certain answer and decide which one makes the most sense and go with that one. And so he's having to do that, so I'm not surprised that he hasn't been able to make an announcement about May 1st, this Friday. So let's pray for Governor Holcomb as we go. All right, so now there's a great example of a molecule that forms with carbon. There's this carbon tetrachloride molecule at the top of page 564. What that means is a carbon reacted in a molecular bond with 4 different chlorine atoms. You'll notice carbon right here wants 1, 2, 3, 4 electrons to have 8 electrons in its outer energy level. So carbon enjoys it when it has 4 different chlorines around it and in a chemical bond with it. Chlorine is, of course, wanting 1 electron from carbon, and so carbon is able to make carbon tetrachloride with chlorine atoms. And it's an awesome thing when you stop to think about it, the fact that these different elemental atoms can form a carbon tetrachloride atom. Okay? And then there's, you'll see where 1 of the 4 atoms attached to a carbon on the next one has a hydrogen instead of a chlorine. So there's 3 chlorine atoms, 1 hydrogen atom, and 1 carbon atom, all bound together with a shared electron between carbon and hydrogen, and carbon and the 3 chlorine atoms. So carbon is sharing 4 electrons. Each chlorine is sharing carbon's electron with itself, and hydrogen is giving an electron, and carbon is giving an electron to hydrogen as well. So 2 different molecules form depending on the atoms that are attached to the molecule. And I can assure you that trichloromethane is much different in terms of its chemical properties than carbon tetrachloride. All right, writing formulas and naming compounds. That was 2 examples of naming compounds right there. Okay, so you usually start with what would be the more positive element, these over here, these become positive because they give up electrons, and these become negative because they receive electrons, these nonmetals primarily, okay? And so you put the highest oxidation number element first in the chemical name, okay? And there's lots of examples of this in this book, writing formulas, okay? Let's look at example problem 1 on page 567. Let's see. Determine a chemical formula. What is the formula for lithium nitride? Okay? So lithium is needing to give up 1 electron. So we're here in that column. You can look up lithium on the periodic table and determine that yourselves. Formulas for lithium nitride. List the knowns, symbol, and oxidation number for the positive ion lithium. So lithium is going to have a positive oxidation number. Okay, lithium is going to become positive 1 if it gives up an electron to nitrogen, right? So nitrogen is going to, it wants 3 electrons, so it's going to become 3 minus. You can see that if you look at the nitrogen diatom, it chemically bonds with another nitrogen, 3, and shares, there's a total of 6 electrons being shared. So nitrogen actually wants 3 electrons to come and be part of its atom. I'll show that to you on the periodic table. There's nitrogen. So 1, 2, 3. It wants 3 electrons. So the periodic table is a handy thing. It can help you to understand oxidation numbers, and it can help you to understand how many lithiums are going to react with nitrogen to become lithium nitride. Okay? So you know that lithium is +1 and nitrogen is -3, so there would need to be 3 +1s with the 3 minus of nitrogen in order to make lithium nitride be neutral. So what you find out is that 3 lithium atoms will combine with the nitrogen atom to form lithium nitride. Okay? So you can check the answer by determining whether your compound is neutral. The charge on 3 lithium ions is 3+, and the charge on 1 nitrogen is 3-. The compound is neutral, so the formula is correct. Okay? Let's do number 14. Let's do practice problem number 14. What is the formula for potassium sulfide? Okay? Well, where's sulfur at on the periodic table? Sulfur, S, is right here. Okay? That's sulfur, and it wants 2 electrons to have a full outer energy level. And potassium, that was the other word, potassium is over here in column 1. It wants to give up 1 electron. So potassium is going to become +1. Sulfur is going to become 2 minus. Right. So potassium is +1, sulfur is 2 minus, so you need 2 potassiums to neutralize, if you will, the sulfur's, what's that called? The oxidation number. So 2 potassiums per sulfur means K2S, okay? Or potassium sulfide, K2S, okay? So you need 2 potassium atoms for 1 sulfur atom. Let's celebrate. Woohoo! celebration? Awesome. Okay, number 15 on page 567. We've got, what is the formula for calcium chloride? Well, hey, calcium chloride, I think, was in this book, back here. We had 2 chlorine atoms attached to a calcium, right? No, I'm just remembering it wrong. Okay? So calcium will become 2+. There's calcium. Calcium is in group 2, or the alkali earth metals, and it will be a 2+. And then, what is the formula for lead phosphide? Boy, that's a hard one. Lead 4. When you see that 4 in parentheses, that's a signal for something. Lead, Roman numeral 4, phosphide, means that lead is +4. It's a metal, lead Pb. Let's see if we can find it on the periodic table. I have to turn around. Pb. Is it over here in the metalloids? Probably not. I am having a hard time finding lead though. There it is. Lead. See lead? Lead's awesome. Pb, right here. Okay? So lead will either be +2 or +4. I don't know if you can see those little numbers on this particular periodic table. Sometimes those numbers are on a periodic table. Sometimes they're not. But lead will be +4. So lead 4 phosphide, which is right here, okay? It's tricky because it's either -3 or +3 or +5. So we've got to use the negative. We know we have to have a negative phosphorus element because lead is +4. So how are we going to balance something that's +4 with something that's -3? How are we going to balance something that's +4 with something that's -3? We've got to find a least common denominator, if you will. So lead is +4 and phosphorus is -3, and is 12 the slowest number? I think so. So you're going to have 3 lead atoms and 4 phosphorus atoms to come up with a neutral molecule. So it's lead, Pb sub 3 with a phosphorus, P4, P sub 4, okay? So you need 3 leads and 4 phosphorus atoms. So there's actually 7 atoms in lead 4 phosphide, okay? That's how that works. We'll practice that a little more probably as we move into the standardized practice test of this chapter. Okay, so then you talk about naming of things. Oxide, you notice we've been using the "ide" instead of talking about oxygen. We talk about oxide, or phosphorus, we talk about phosphide, or nitride, or sulfide, etc. So you have chloride, fluoride, all these halogens have an IDE, bromide, iodide. That means they're not in elemental form, but rather they are in a molecule. And typically, all the nonmetals are reacted with a metal. Okay, sometimes nonmetals react with nonmetals, especially when you make diatomic molecules. Okay, so then there's also, in addition to one atom reacting with another atom, we've already talked about the fact that multiple of atoms of one element will react with multiple atoms of another element. Sometimes you have complex ions, okay, that react with one of these or one of these. for example, calcium carbonate. So you see their carbonate name down here on page 569 in table 4, the polyatomic ions. You could have a calcium carbonate. Notice carbonate, CO3, is a 2 minus, and calcium is a 2 plus, and so calcium carbonate is a molecule. And I wish we were all in a classroom together and I wasn't sitting behind drums and I could use my whiteboard a little bit. But I think you guys get the idea enough for me to know that elements react with each other to form molecules. And you can actually name molecules without too much trouble if you study the naming conventions, etc. Okay? Okay. So I think my next video is going to be about the standardized test practice. We're just going to go through the standardized test practice in my next video. And I hope this was beneficial. Don't forget about the bell ringer. It's in a different video. And know that I love you and I'm praying for you. And let's actually wrap it up in prayer. Heavenly Father, you are with us. You will not abandon us. It's a strange time that we're in. There's a lot of things going on. Depending on who you listen to, you could imagine that things are very ungodly, is how we are here now. And it's not necessarily your natural world is causing all of this. We are needing you now, especially. We're missing one another as students in classrooms and teachers. We're enjoying our time, I'm sure, if we're doing what you want us to. And so I do thank you very much for helping us to help others. In your mighty name, Jesus, amen.